Okay, so this week's lab, we're going to be looking at potassium permanganate and trying to determine the percent of hydrogen peroxide in a store-bought bottle of hydrogen peroxide. One of the first things we have to do is we have to standardize our solution against a Mohr salt in order to figure out what our actual concentration is of the potassium permanganate. So, the equation that we're doing in regards to the potassium permanganate and the ferrous ammonia sulfate hexahydrate is what's underlined with the yellow marker. And you notice it's a very long equation. And I'm going to show you why we're going to step away from that type of equation and we're going to focus on our net ionic equations in order to understand what's going on in the reaction. Okay. The point of this lab, we're doing a titration. It's a little bit different from an acid-based titration, even though we are using an acid to help the reaction to occur. We are doing a titration on a redox reaction or an oxidation reduction reaction. Oxidation reaction always come in pairs together. And oxidation reduction reactions just means that my electrons are being exchanged. Someone's losing electrons and someone else is gaining electrons in the reaction. A quick way to remember the terminology is LEO-GR. LEO stands for lose electrons, oxidation, and GR means gains electrons, reduction. And a quick note, oxygen does not have to be present for it to be a redox reaction. Okay. So we're going to re-examine our reaction, and we see that I've shortened this down quite a bit. That's what the blue reaction represents. And I focus only on the ones that are actually reacting and not the spectator ions. So we have our iron that's reacting with the manganate ion. And they are reacting to a 5-to-1 ratio between the two. So we've done a titration and we found that our equivalence point is 9.214 milliliters. And since I was titrating technically I should be titrating my known into my unknown, which means the potassium permanganate should be in the beaker down below. My equivalence point actually means the volume of the FAS salt. So just a little clarification there, a little different from when I set up for our lab. And so I started with 10 milliliters of my potassium permanganate. Now, my equation that I'm using is this M1V1C2 equals M2V2C1. So my M1 for the FAS for this example is 0.100 moles. My V1 was at equivalence point, which is 9.214 milliliters. And my C1 is a 5 because it comes from the equation above, and that's the number that's in front of the FE. So again, I use 10 milliliters of KMnO4, that's my V2, and my C1 is a 1 because it comes from the equation, and there's a 1 in front of there. Once I have that, then I'm going to plug them into my equation. And I have to remember that I have to make sure that I do M1V1C2 equals M2V2C1. Once you perform the calculations, we're going to get 0.0184 molar for this example here. Okay. Now, once I have that, and I've either run a second titration to verify that number, or I have verified it maybe with the class to check to make sure we are titrating correctly, then I can proceed forward and I can do my reaction between the potassium permanganate and the H2O. With that in mind, my equation is a little bit different because now I'm going to focus on the H2O that's occurring in the reaction. And so my reaction has now changed a little bit, and I have a 2-to-5 ratio between the manganate ion and the hydrogen peroxide. Now, in this setup, just like in your lab, We diluted our hydrogen peroxide. This example, I'm going to dilute it to 1/10 normal strength. So I take 10 milliliters, place it in a 150 milliliter beaker. I'm going to place 4 milliliters of 4.5 molar H2SO4 and then 16 milliliters of distilled water, H2O. And when I do this run, my equivalence point with the KMNO4 is 15.464. Now, since I'm now running with the potassium permanganate as my known, that's what's in the burette, and so that reading becomes KMNO4's reading, okay? And again, my molarity comes from the standardization that I just did, which is 0.0184, and my C1 comes from the 2 that's in front of MnO4 in the equation. For the H2O2, I use 10 milliliters of it. M2 I do not know, and again, my equation, I have a 5 in front of the H2O, so C2 becomes 5. I'm going to place this into my equation. M1V1C2 equals M2V2C1. And again, make sure that you're careful to keep track of who you're putting for who. And when I do this, I get 0.0711 molar. Now, what does that even mean? Great, I've got a number. Now, what do I do with it? How does this get me back to figuring out what the percent of hydrogen peroxide is in that bottle? Great question. So we have to understand what that 0.0711 molar means. And a few things to keep in mind, we diluted it to 1/10 of the original concentration. So my molar concentration of 0.711 capital M also means 0.711 moles per liter. What else does that mean? Well, if I look to my periodic table, I discover that H2O2 weighs 34 grams per mole, and I can take that number times 0.711, and I get 24.17 grams H2O2. Well, that's great, but that number means that that's per 1,000 milliliters. So if I do the math there, then I get 2.42%. And the bottle says 3%. So this tells me, based on what I've calculated, that this is lower than the percent that is being advertised on the bottle. And so these are the calculations that you guys are doing for this lab as well. Okay, so I've given you some examples to help you work through that, and good luck.